So our talk will start at 1 p.m. and we have a backup room for overflow, 305. So if you can share the room 305. And today there is only one talk here in this afternoon seasons. So the other professor cannot come to Bimsan. And good afternoon, everyone. So welcome to the afternoon season here in A14304. My name is Jia Kang, and I will chairing this afternoon seasons. Before we begin, so let me introduce our speaker today. So the speaker is Professor Johannes Schmidt-Hieber. He's a full professor of the statistics at the University of Twente in Netherlands. And his research interests include statistics theories for deep neural network and non-parametric regression and Bayesian method. So welcome, Professor. So the talk title is Towards Statistics Foundation for Machine Learning Method. So welcome.
Okay, thank you very much for the kind introduction. I'm very happy to be here. I think it's a great event, a nice idea to bring the whole basic science community together. And I also try to set up my talk in such a way that it's understandable for everyone, at least partially, and not so much talk to a specialist. If you have specific questions, you can ask me either afterwards. There's also enough time if you have a very urgent question to interrupt me. I also want to thank the organizers, of course, and the city of Beijing for supporting all this. And one thing before we start, what I want to mention, so if you're interested and you have a background in this field or in mathematics, also feel free to contact me if you're looking for positions. So we have tons of PhD and postdoc positions, and so just feel free to either contact me personally or drop me an email. Okay, having said that, so what's my FSA paper? It's on something that has basically started a whole line of research, something that kept me busy for the last 5-6 years. And so what I want to do today, I want to not only present this paper, but give you the whole overview. And that is articles that I have joined with a diverse group of people spread all over the world. I have a couple of collaborators in the Netherlands. Some of them are in my group, people from France, from Chicago, from Japan. And so that's a very international effort as well, what we are doing here. So what do we mean actually with statistical theory for machine learning? So what is statistical theory? So what it means, like, if you just do machine learning, then you're given an objective function, training class, and that's the whole goal is then about minimizing that, and then you study gradient descent methods or versions of that, and that's it. If you do statistical theory, there comes an additional thing, is that you model the underlying data. So you assume that the underlying data were generated from some mechanism that you specify, and this mechanism has some unknown, say an unknown function in it or so. And then you study, assuming that the data were generated from this model, you study how well a machine learning method can reconstruct or learn then this underlying object, say the target function. And so that makes it specific. And of course, once you can do that, so you can see like on say benchmark models, how well deep neural networks can perform. Now you can wonder, okay, so mathematical statistics is around for 100 years, starting with say parametric models and non-parametric models, and so why can't we just apply these techniques that we developed in the past 100 years? Why can't we just apply that to neural networks and we view neural networks as a statistical method, right? We have data, we have a neural network, we fit the neural network to data, so that's statistical method. Well, the reason is that the existing techniques are by far not sufficient to analyze neural networks, because neural networks have very distinctive properties that make them statically almost intractable. And so first of all, like what we like to analyze and somehow linear methods, and you can do a lot of things explicitly as well. Um, neural networks are nonlinear methods. They're often described as some sort of black boxes because we really don't understand what is going on inside them, how these parameters are assigned. So that's certainly maybe the most difficult thing to deal with. Another thing is that they are high-dimensional, another challenge that are high-dimensional, and so that means you have to give more parameters than samples. So you have over underspecified problem, and the question is like then, yeah, so how can such a thing learn? So we have high-dimensional statistics, so in principle we can try to blend them together. Then there's this other thing is that these machine learning methods, they perform extremely well on inputs that live on high-dimensional input spaces, and so for instance images. And like the classical theory that we have developed that tells us somehow function learning, if the function is defined on a high-dimensional input, then this becomes very, very hard. And so basically it's impossible with the standard assumptions that we make. So then there's always the question, how can neural networks somehow circumvent or avoid this curse of dimensionality thing? Many other things that one can study with in such a statistical theory. For instance, you want to understand these empirically found phenomena such that, for instance, you just over-parameterize until you have almost zero training error. How can you still generalize well what has been observed in empirical studies, right? So how can you explain that theoretically? There are also other things like data augmentation, where you just somehow you reshuffle your data, you transform them a bit and put them back into your data set, and then you train on the augmented data. That is also something which we don't really have existing theory yet on, and that's just all like things people like via engineering approaches, they have figured out that it somehow works better, and we really can try somehow to understand how that can improve and derive theory for that. And there are more things maybe you have heard about this squawking phenomenon, which is also very, very counterintuitive from a practical perspective. And so we want to somehow build a theory that can explain these phenomena. And one more thing is another challenge is that, of course, there's a lot of things that come together here, and just fitting a neural network will not perform very well on empirically. So there's many things to regularize the training, and only all these things together somehow that gives you a method that then leads to state-of-the-art results. So we have somehow to take that into account, and this things on regularizing on the fly while you do gradient descent, like this algorithmic regularization, that is also something that has not been really explored within the mathematical statistics community. So many things that have to be done. And so now I will follow these challenges, and then I will show like how we can deal with individual challenges or some of them combined. Okay. So let me start with the definition of what a neural network is. You probably all know this. So a neural network is just a way to write a function. So here it's a function with an input vector, say a d-dimensional input vector. And then so you have a weight matrix W0. And so you have here matrix vector multiplication. So that gives you a vector. And then component-wise, you apply this univariate function sigma that is pre-specified. So in modern neural networks, you take a value, or now even more modern, you take CLU or so. So you apply the component-wise to this vector, and then it still gives you a vector. And then you just iterate this procedure L times. So you always do matrix vector multiplication and then component-wise application of the activation function. And after L times, so you have an output layer, say in a regression case where you don't do anything with that. And that gives you then the function class. And so here we will mainly, or basically talk about these value neural networks. And so they generate, and you can easily check that always generates piecewise linear functions in the input variable. So you can also represent them as a graph, but if you like to do mathematics, it's better to write them in this form. And here you can also see how that generalizes, say, the standard linear model that we like to have. It's a nonlinear extension of that. Now, these matrices are quite large, and the deep learning is a way that given data, you specify a loss, say the least squares loss, and then you somehow put a function of this form to your data. That means all these entries of these weight matrices, they are the free parameters, and that can be in the millions or billions or so. And then you try somehow to adjust these parameters in such a way that these inputs, if you stick in here an input, that this corresponds or gets close to the outputs on your training sample. That's what happens underlying the deep learning, that you somehow try to find the function of this form that resembles the input-output relationship. Now, one thing which is impossible, and that's basically when I started this in 2016, and so these computer scientists say, well, you can't do any statistical theory, because if you want to do statistical theory, you would have somehow to understand, given a data set, you have to find somehow formulas that tell you how these weight parameters, what they will be after the training procedure, and that will be somehow functions on the data set. And because it's all very nonlinear, you have these sigmas in there, there's no explicit formulas. So that's like really this idea that you have to open the black box before you can really say how well a method performs. But of course, for statistical theory, that's not really a problem. So we have statistical learning theory. And so by statistical learning theory, we don't really need to know how these parameters are, what their values are. So all what we have to know is somehow that these functions, they perform well on the training sample with respect to the training loss. And then with a couple of other properties that we have to check, we can use empirical process theory and then derive the statistical convergence rate. So that's a very powerful tool that we can still apply, although we have this nonlinearity. What's the drawback of this approach? The drawback of this approach is basically that we can only say something about the network that would occur if we can train the neural network to a global minimum, what we call the empirical risk minimizer, because it minimizes the empirical risk or the training loss. And we cannot really say anything about the trained neural network via gradient descent, and this thing on bringing statistics and optimization together, that is still open more or less still until nowadays. But we can do something, we can say something about the trained method that is computationally not feasible, but it gives you some sort of insight about how all that works. So that's one way to deal with this nonlinearity. The second thing is the high dimensional. The second challenge that I mentioned is that's high dimensional. So this is a plot. Here you see the early network architectures. For instance, the AlexNet, so the architectures, and the size of the disk corresponds to how many parameters these networks have. So the AlexNet, for instance, has 60 million parameters and was trained on 1.2 million training samples. So you have more parameters than samples. And on the right side, you see that somehow this is on a log scale, somehow fitted. You see some form of linear relationship in here. So as time grows, these networks just become bigger and bigger. Now these transformer models, you can argue they are maybe not high dimensional anymore, but there's a certain regime of where we indeed do have these high dimensional architectures. And so what I mentioned before, we have high dimensional statistics, and then we can use tools from high dimensional statistics to deal somehow with the fact that we have more parameters than samples. And one way to do that, the most straightforward way, is then we just say, well, there are potentially many, many parameters, but most of them say are zero, and there are only a few non-zero ones. We don't know where they are. So that would correspond then that these weight matrices that we have seen on the previous slide, that they are sparse matrices. Okay, so we can just add a sparsity constraint and say somehow there's just some sort of low dimensional structure underlying, and then we can still apply these results from high dimensional statistics and say something meaningful about neural networks. And this is addressing these two challenges that I mentioned on the previous two slides. First of all, the nonlinearity in the networks, and also the high dimensionality. And this is actually the paper that has been selected, so the main result in the paper that has been selected for the FSA award. So what we do is, so I said we are statisticians, and we first somehow assume something about the underlying data. Okay, so we assume that we have n samples, they correspond of input-output pair, so this is the nth input and that is the corresponding output, and they're connected by the so-called non-parametric regression model that says that the outputs are, that there's a function that transforms the inputs to the outputs, but the outputs on top of just the function, they're also corrupted by some noise that can account for measurement noise, but also for all sorts of variables that were not included. There might be, like the xi's might be not fully informative for the yi's, all sorts of things that can go wrong. Okay, so that's something we just assume, like the data were generated from that mechanism. It has nothing to do with neural networks. And then once we have such a model about the data, so the interesting thing is then once we fit a neural network, how well can the neural network learn this underlying function, right? It has only limited information because we just have n data points from that. So we don't know the full function. There's also information static limits that tell us like how well it potentially can be done by any method. And then we want to know for neural network, how well can it basically learn this function. And so the result now is that if we take a sparsely connected neural network to account for the high dimensionality, and otherwise there's no constraint really on the number of parameters. It can be really, really wide. We can have in principle e to the n parameters, so n is the sample size. But the sparsity, that's really the crucial thing, and that has to be carefully chosen in order to get this result. So that's really the thing that drives the regularizing mechanism in the neural network. And then what we do is, I said before, we can only do empirical risk minimization, but here in this result, we can do a bit more. We can say, okay, so we take any procedure, which we call f hat n, so it's based on the data. That's what does such a procedure do? It takes the data set, right? These n input-output pair. It doesn't know the function f, of course. It just knows the data. And it spits out a neural network that is sparsely connected, and the sparsity is chosen in a certain way, also the number of layers, and the width is chosen, but the parameters are otherwise free. Okay, so it can be gradient descent, can be anything you like. So it's just something that takes the data and spits out a neural network. So what we can say now about this is the statistical risk, or we call it the generalization error. That is basically how well this function f hat n approximates this unknown function f, and then we measure that in a prediction sense. So what we want to do with these machine learning methods, we want to predict on new data. So assume x is a newly generated random vector from the same distribution as the data. So then we want somehow which f and hat should then predict the corresponding response, which we don't know, right? So we want to know is the image a cat or dog image or so. And then we compare that basically to the truth. And so we want that to be close. That's the thing. And we measure that in expectation because we want something deterministic on the left side. And so this generalization error, we can show that up to log n terms, which I ignore here because the main terms are somehow polynomial in the sample size, up to these log n terms, there are two terms that determine this rate. The first term is the phi n, and that's the so-called minimax estimation rate. That is really the information static optimum, what you can achieve in this model in terms of convergence rate. So that means not really the constants, but really like the rate in the sample size n at which this tends to zero because the more data we have, the more information. So that should somehow converge to zero. And then we have a second term on top of this. And the second term that has something to do with, well, like how well this method does. Okay, so here I said I can take any method that takes the data and spits out a neural network. For instance, it could not look at the data at all, and then it cannot learn anything useful. Or it could do something very, very clever with the data and gives me a neural network that includes somehow all the available information about f in the data. And so that's somehow decoded in this delta n. And it's basically what the delta n measures. It measures what is now called the optimization error. So it measures something, an expectation between the training loss and the loss of the empirical risk minimizer. So that's the training of the global minimum. So basically you can think about what we call the energy landscape. So for every f, we get a loss, and there's a global minimum that sits somewhere here. And then, so if you reach with your function, you reach, maybe you can also draw it on the board if there's some chalk. Yeah. Looks like this. So you have here the energy landscape is somehow the function that sends here a f to the training loss. This is this function. It has somewhere a global minimum that sits here. And now suppose you have your training mechanism and it runs gradient descent, and gradient descent will bring you in here, then this delta n measures this difference. So that means if you always end up in the global minimum, then delta n is 0, and otherwise the delta n somehow measures it. So that means if you, for instance, don't train at all, right, all these gradient descent methods try to bring you down in the energy landscape. If you don't train at all, delta n will be large, and that will dominate the right-hand side. And it's also from below, so it's not only from above, it's really like asymptotic in terms of these rates. So that means what we want is good rates. That means we have to bring this delta n, this optimization error, at least as low as the phi n, and then we achieve a minimax rate optimal procedure with these sparsely connected neural networks. That's what it tells us. Okay, so then if you do the analysis, there are certain things that naturally pop up. One thing, and I omit some details here also in the way the result is formulated, but one thing that naturally comes out of the analysis is that you should take the number of layers, the depth of the network, that you should take it of the order of log the sample size. So that's maybe something which you would not expect, that there's some sort of scaling. That means the more data you have, the deeper you should take your network. But if you analyze this, you can see then, so what happens is that this hierarchical structure of the neural networks, it allows you, it's always a piecewise linear functions in the input, but by adding layers, you can basically double, in certain cases, you can double the number of pieces. And if you take log n layers, you can go to something like a polynomial number of linear pieces. And that has very favorable statistical properties. In particular, it allows you to get optimal weights for arbitrary smoothness, which is typically hard for other schemes. So if you have something which is just piecewise linear, it's typically impossible to get the optimal weights if you have a very smooth target function. And by doing this, but there are also many other reasons to choose this log n depth, and that's something which you can see coming out of the theory. And since this paper is around for many years now, and I think basically that has stayed like that all the time. So people just always didn't find another way to do it differently. And I think that seems an interesting conclusion from the mathematical analysis. So now, typically someone will now raise the hand and say, well, what about the sparsity assumption? We don't have really sparsely connected neural networks. We train densely connected neural networks. And that bothers me a lot, and it had a lot of discussion. First of all, there are many ways now also to sparsify neural networks. For instance, as a post-processing step, it's very, I mean, it's nice to have sparse neural networks because they consume less energy and so on. And the compression rates are quite amazing. So people on the standard machine learning benchmark sets, they manage, like, out of 200 parameters, they manage to set 199 to 0 without really a loss in performance. So the denseness is a nice feature that is important for the learning, but once you have a trained network, you basically can reduce the number of parameters quite dramatically. But of course, it does not fully align with the theory, and you want to understand what similar results also hold if you just allow for densely connected neural networks. And here's a counterexample that shows this is in general not the case. I don't say this is the full answer to that, but that shows you somehow if you would allow for densely connected neural networks, what will happen? Okay, let me take you through this plot. So we have this red curve is the underlying function that we don't know, that we would like to learn with our neural network. So that's the red curve. Now these blue dots, they're noisy versions, right, generated from this non-parametric regression model. This is our training data. This is what we get to see, the blue crosses here. So now based on these blue crosses, we fit our neural network. And now we take a shallow neural network, and we can even mathematically analyze what is going on if we take a very, very wide shallow network and then just train the outer layer, and we do some assumptions on the initialization, a bit like in the neural attention kernel. What is going to happen is then that this neural network, this overparameterized neural network, it will converge to the orange curve, which is not a good fit for the red curve, right? So it's not getting close, it's even inconsistent if you want. So it cannot really do the denoising that you have to do here. And one can even show that in this case it will convert to the natural cubic spline interpolance. It's an object, and it's interesting that it does that, but it's not a really good fit for the red curve. So if you have noisy data, then somehow you have to tell the neural network that it has to do some local averaging, like some form of smoothing, and you cannot do that via inducing sparsity or maybe low rank assumptions on these weight matrices, but not by just putting nothing, right, and just training. So in general, you will then end up with something that is not even a consistent reconstruction of the underlying red curve, which you can argue maybe for prediction that's not so important, but if you go for the function estimation, then it's not going to work. So you need something for noisy data. And I will come back to this point later in my talk. Now, this third challenge that I mentioned is how can neural networks avoid this curse of dimensionality, right? So they really strive on high-dimensional input spaces, say images or text data or whatever we have. So where you have inputs in a 1,000-dimensional space, and they can still come up with amazingly good predictions, which means somehow there's an underlying function learning problem that is you live on the function lives on a 1,000-dimensional space, and so you would have to estimate such a function. So why is that hard to estimate such a function? Well, because these high-dimensional input spaces, they're basically empty. So if we draw endpoints in such a, say the inputs are contained in a 0, 1 cube in RD, then the distance between 2 points in the input spaces of the order n to the -1d, if they're more like mostly uniformly distributed, and that gets worse as the dimension increases. And so what we need for all these function learning problems, we like to look at neighboring information of a point, right? So, but if the neighbors are very far away, then this is very weak information. So that makes this function learning problem extremely hard. And these convergence rates that we have to just scale down with the d, and if you have the convergence rate n to the -1/10, so that it basically says, like, even for these huge data sets that we have for training neural networks, that means somehow it's not going to converge ever. So how then the question becomes, like, what is the mechanism that these neural networks can somehow circumvent this curse of dimensionality? How can that actually be? I think by now many people have worked on that, and I think we have contributed to 3 ideas in this direction. There might be different mechanisms. So the first one is that there is somehow more structure in this function learning problem that we impose on the data, okay? So that these data sets where neural networks perform well, that they have additional structure that is somehow picked up by the neural network, and that allows the neural network to circumvent curse of dimensionality. So that's this part. And then the second part, which I also want to talk about, is that somehow one has to think about a completely different way about the modeling side of the data, and that makes the curse of dimensionality also to disappear. And so I want to talk about all these 3 things, and let me first go to the non-parametric regression setting that we have discussed before. And that is just the way, what we assume how the training data were generated, right? So these classes, they are now called compositional sparse classes. And so what are they? So we have this unknown target function in our data generating mechanism f. And what we assume is that this function f is generated by a composition of functions, g0 to g cubed. Q can be something 10 or 5, it doesn't really matter. It's another parameter in this function class. And so those are vector valued function. And then the assumption is that each of these component functions of these functions, each of the component functions can only depend on a few variables. Okay, so like in an additive model, or so you just have a function where you can write it like component functions, and then each component function just can say depend on 1 variable or 2 or so. So these functions, maybe G0 can map in a 1,000-dimensional space, but then G1, each component can only take 3 variables or so, and then because there are many components. They can pick up all the 1,000 variables, but not all component function, not every, like no component function can depend on all the 1,000 variables. Okay, so first of all, I want to say this includes many structures that we have imposed, like additive models or generalized additive models in non-parametric statistics before and have been analyzed in a general form. We are not interested in somehow recovering these component functions. That's not the thing. It's just something that helps us to make it easier to learn this function, f. And what one can show is actually that if we assume that, then because neural networks, now this has nothing to do with neural networks, it's just something like what we assume how the data were generated. But then these neural networks, because they also have a compositional structure, they can pick up the compositional structure in this function f, and then they can learn that with the optimal convergence rate, which one can show that in these cases does not necessarily, or in certain regimes does not depend on the input dimension, at least not in the convergence rates, maybe in the constants or so, but not in the convergence rate. So that if the function is of this form, then one can really prove mathematically that neural networks can pick that up and can, under certain conditions, have a fast convergence rate. Now you can want to set a reasonable assumption for, say, these standard machine learning tasks where neural networks are state of the art. Well, I think there's many things in the world that are built up based on composing smaller blocks, right? You can, it looks a bit like a sort of a computer program or a little algorithm, right? Where you have small modules and then you somehow combine them and so on. And there are just many things that have such a modular structure, and where one can argue maybe that at least to a certain extent, these things are present in and somehow underlying these tasks. Or also people think about nowadays these causal problems where like you want to show that smoking causes lung cancer, but it's not that smoking causes lung cancer. It's like smoking causes something in your lung, and that causes another thing, and that causes another thing, and so it goes via a chain until at some point somehow that causes your lung cancer, right? There's many things in between. But we just see basically the start and the end, just see somehow the input and then the full composition. And that just seems to underlie many things, that many learning problems that we have nowadays. And the result tells you now, if that is present, neural networks have the chance to pick that up. I also want to mention that in this paper, we showed that wavelet thresholding estimators, which are considered to be typically good for all tasks in non-parametric statistics, because wavelets have a certain way to decompose function spaces, which is quite optimal in many ways. They cannot get the optimal rate. One can really show that they, in certain cases, they really suffer from this curse of dimensionality phenomenon, because wavelets, this is a linear expansion of your function space, and it cannot really see these compositions in the functions. So these wavelet coefficients, everything is based on the wavelet coefficients. In the wavelet coefficients of such a composition, they will basically behave as a function that has no composition. So you cannot disentangle based on the wavelet decay of the wavelet coefficients, whether there was a composition or not, and on which one. And therefore, so they have no chance, and one can make that actually rigorous, which is interesting because that was or is considered to be a method that basically works for all sorts of function learning problems. But if there's compositional structure in there, that is apparently hard for these wavelet methods. Okay, so here's this compositional sparsity. I just want to show you one paper by Tommaso Poggio, which is the main figure in this deep learning field, that he says, like, basically compositional sparsity of the target function is somehow the leading key principle in machine learning. I wouldn't go that far, but I think there is certainly something like it's somehow a mechanism that is probably realistic to assume that underlies to a certain extent these learning problems. But there's more to it. How else could neural networks circumvent the curse of dimensionality? Another thing that is probably true is that the task that we have, say you want to classify dog images or so, and these dog images lie on on a low-dimensional manifold, and people try to estimate the manifold dimension and so on. Oh, sorry, this is okay. Shy. Okay, shy. Okay, that's my family. Sure. Good. I think they just woke up. Okay, good. Anyway, so that they lie on a low-dimensional manifold. And so what does that mean now is that these xi's, these inputs that we have, they lie in a high-dimensional ambient space, the space that is generated by the number of pixels, that's the dimension then, but somehow on a low-dimensional manifold in this high-dimensional ambient space. And then what is the neural network should be that they should depend on the real dimension they should depend on is not the ambient dimension, but the dimension of the manifold. And that should be the driving dimension. And so can they pick that up? And basically that's, you can rephrase it. Sorry, I don't really know how to turn off my phone. I have a new phone. And I don't know how it works. Okay. So what drives that is that basically you can rewrite this whole thing as also some compositional thing, because you have a chart that maps from the manifold to RD stars, D stars, the manifold dimension, and then the second function that you want on top of that. So it's a composition again, and you can trace that in this framework, and you can show that neural networks, if there's the data lie on this manifold, that it can pick up the structure and can also depend only on the manifold dimension, not the dimension of the ambient space. And it was very unfortunate because when I published this, like I think everyone in the community knew that this would be the next thing to do. And then there were other people that were, I think a week earlier on arXiv, and actually they had a stronger result. So in the end I put it on arXiv, but I never published it because I think it was basically the same thing. Actually their paper was even a bit better than mine. And that's something like what I learned from that is to stay out of these things where everyone knows somehow that's the next one. I'm not the fastest one, and then probably they will always beat me. It's better to go to directions where no one is. And that's maybe one thing which we also did. And that's the third thing that we really try to try a completely new way to model the data generating mechanism. Because, you know, like this is the first problem where these neural networks became state of the art, and that started this whole deep learning hype is image classification. You get to see, say, 1,000 pictures with elephants on it and pumpkins and so on, and then based on that, you try to teach the neural network how to distinguish between elephants and pumpkins. Whereas the model that we propose and that we like have a standard benchmark model for supervised learning, or learning with labels, is this non-parametric regression model. And the non-parametric regression model, if you phrase it in, let's say, the imaging framework, that corresponds to denoising, right? You have on every pixel sits a noise, and that's what you get to see. And based on that, you want to recover the clean image. So if you compare these two tasks, image classification to that, you see that it's a very different problem. So what you want to do instead is you want to propose a new model that somehow much better resembles that, and the hope that you also the other empirically found effects in deep learning that you can also reproduce them by theory, because somehow you get stuck, and that's like artifacts that are introduced by the model that becomes then important. For instance, the sparsity, you will see that later, has to do with this denoising. If we go to another model, then sparsity is not necessary anymore in these neural networks. Okay, so it's something I worked on a lot, and I continue working on a lot. So how do we then model that, the image classification? Well, we can still use this machine learning perspective, and the machine learning perspective tells us, well, the dimension of the problem is the number of pixels, and there's somehow an underlying function f that we don't know, and that whenever we stick in one image, say a dog image or a cat image, it will return us the correct label, say cat or dog, right? And that's the thing we want to learn. That's how machine learners think about this problem. But then you have this issue that it's because of dimensionality, the more pixels you have, the higher dimensional this X space, and so the harder it gets to estimate the function, which is quite counterintuitive, because you would think a higher resolution should tell you more about the image, and it should make it harder, right? It should make it easier somehow because you just have more information about whether this is a cat or dog. And so instead what we do is now we take this imaging perspective, and then all these dimension dependence is basically gone, where we say, okay, an image is just a two-dimensional object, and a pixel is an image that is a matrix. The image is a matrix, and every pixel is an entry in this matrix, and the JL's pixel value is given in this form. So we have an underlying intensity. This is like the pointwise intensity, and we just average over the pixel region, and we normalize it such that it gets measure 1, and that gives us the pixel value. And now the thing is basically it's driven by this underlying function f. And the f is now just a two-dimensional function, so there's no high dimensionality anymore. But of course, there's no image classification yet because we just have one function here. So somehow we have now to augment our approach to allow for image classification. So how do we do that? Well, this is what I just said on the previous slide. So this is how we can write an image. And so we call these f's, we call them template functions. And then I will show you that by changing the function that will somehow lead to deformations of this image. Okay, so for instance, the template function could correspond to the way this this handwritten 4 is, and the values correspond to the gray values in this image. Say white ones are large values and black one is 0, and it's decoded as function values. Now, if we, for instance, if we multiply here with an eta, which we can call like a sort of brightness parameter, then what happens is that by changing this eta, we make the 4 either a bit brighter or a bit darker, and so that increases a bit like the variation in this image. We can also introduce shifts, right? We can introduce a tau here and a tau prime here, and that makes the image to move, the 4 to move on the image, right? So if we change the tau parameter, so if we can move the 4 all the way across the image, we can also introduce scaling here. So this is scaling in x and y direction. So if you have an xi that is larger than 1, then this will shrink the image and otherwise stretch the image in the x and y direction. And so you can see you can also add variation in that sense as well. Okay, just by adding parameters to that, you can get somehow to a certain decent amount of variation. So now this is, if we do all these 5 parameters, so the brightness, these 2 shifts, and the 2 scalings, then we get somehow something that doesn't perfectly look like variation within handwritten digits, but it has it picks up certain transformations and deformation. We can even make it a bit more general, and we can just say most of these things happen actually in the input of the function f, and not so much on the outside. You could put another transformation here, but we could say, well, an image, a deformed image, has somehow another function a that maps now from R2 to R2, and this function a somehow first transforms our input, and that is then applied to the template function, and then we have this brightness factor on the outside is the only thing just to account for changes in brightness, but one could make it complicated as well here. And so that models now one image deformation. Now, if we have a model for image deformation, we can also write down a model for binary image classification. What does that mean then? So that would mean we have 2 classes, two template functions. They call the template function that characterizes which class it is, say a dog or cat image, or handwritten digit 4 and handwritten digit 7. And then all what we get to see is every image has its own eta and a, which we don't observe, and it's a deformed version of either the 4 and the 7, and we get that as labeled a supervised training set. Okay, so based on that, we then want to learn how well a neural network can do and get generalization bounds for the misclassification error. And so we have done all this, and I don't show you the details because of time reasons, but that leads to a completely new analysis, very, very different, because the learning objective is now completely different. So before, in these non-parametric regression models, so the thing is always the neural network has to learn some form of local averaging, some smoothing or so, because it has to cope with the noise. And so the only way to get rid of the noise is somehow to use neighboring information, and then that will cancel out the noise contributions. But here it's a different thing. So what the neural network has to learn, it has really to learn that the label remains invariant under these deformations, that whether the 4 is in the left upper corner and very small or somewhere in the center, it's always a 4. And that means also the whole approximation theory, everything that underlies the analysis suddenly becomes very different. Allows you also now to analyze convolutional neural networks, which are not new because they have this translation invariance built in. You can't really do that on a non-parametric regression model. And I think with this one, we can basically reproduce all these things, including, we hope, including the data augmentation that is still subject to some additional work, that are observed in practice. Okay, so here I have a comparison for you without showing you all the details in these generalization bounds that we derived. Like, this is what you can do for the non-parametric regression model, and this is for these image deformation models. So first of all, the learning objective is different. I just mentioned that. The second thing is you can apply convolutional neural networks, so we can do that in this case, and then the feature learning becomes important for these tasks. Both of them we have seen that there are mechanisms how they can avoid curse of dimensionality. We can also show that you can just over-parameterize in the image deformation models because there's no additive noise and so on. Like interpolating the data is actually favorable because on those data points we know the truth, right? So there's no additive noise. And so one can show that one doesn't have to put anything like the sparsity that we had in our earlier work. One can also show that zero training error, which is closely related, is beneficial. And we are thinking also that the data augmentation, one can really see how that can benefit to the performance of the method. Okay, so in conclusion, if I would have to start all over again, I probably would not have written this first paper. I would have immediately started with this image deformation thing. And I believe this is also the way forward to understand other network structures such as transformers and so on. It's really on first having a good model for the underlying task and then doing the theory afterwards. I want briefly to talk about this other challenge that we have, because it's something I worked on in the past 2-3 years a lot, namely the algorithmic regularization, which is not very... So how do we regularize in statistics? We typically think about the training loss, and then on top of this training loss, we put a penalty, and then we think about like the minimizer of that objective function. In machine learning, it's different. You do gradient descent, and then on the fly, right in every gradient step, you do something that regularizes, or hopefully regularizes. On top of this, you have this implicit regularization of the stochastic gradient descent. You have actually seen that before in this one plot, which I had where I showed that the SGD converts to symmetric cubic spline interpolant. There's also implicit regularization because value networks are piecewise linear, and then if you go to the limit, you get to the natural cubic spline interpolant, which has somehow a second derivative. So you see that somehow there is some regularizing thing in the gradient descent that somehow means the limit objects are more regular than the neural networks itself. And there are many, many more things that have been discovered by now. What I have been mainly working on is a theory for dropout. So it's a series of works, and we are continuing that. There's actually a third paper that I didn't mention here. So the dropout is a mechanism where you, in every iteration of your gradient descent, somehow you drop out some parameters and you update the gradient on the remaining model. There are all sorts of analogies with biology, and so why that should regularize. It's a very non-standard idea. And so we were really able in the linear regression model to work out and follow this dropout, how that in every iteration step, and then to see how it regularizes actually in the long run. There were earlier approaches which first somehow average out over the dropout, but then you get somehow just what is called the explicit regularization effect by following the dropout in these iteration steps, and really all the randomness, keeping track of the randomness, we also can work out what the implicit regularization is, and you can really see what also has been observed earlier in empirical work, that there is a non-negligible implicit regularizing effect that also remains in the limit, and then you can work out what it is. And so that's something which we did. I think there's one thing which is very important for neural networks to work is batch normalization. No one has ever, in my opinion, no one has ever looked into that. It is completely open yet. With Masaki, I was working on what we call loss surface regularization. The fact that the energy landscape is very, very irregular and has these very deep valleys, that constrains the algorithm in close to a local minimum and has itself a regularizing effect because the method cannot just go in every direction. And something, here's also a paper missing that we just uploaded in an archive. We have been, and Peter Bartlett has an earlier work on that, have been looking at the so-called sharpness-aware minimization, or SAM, which means somehow you also add noise to your gradient descent in order to force the thing to get to a wider minimum, which are believed to have better generalizing properties, and also they're more robust to adversarial noise, which is a big obstacle in deploying image classification in practice, because there's always the possibility of a harmful attack. And so that's another way. Basically, all these gradient descent schemes, they form, with regularization, they become some form of noisy gradient descent. And I think by now we have also a good set of tools on how to deal with noisy gradient descent and also noisy stochastic gradient descent. Now, another direction is we have to do something with the theory. It's nice to somehow rebuild the results, the empirical findings, but it's also, I mean, basically theory has also to contribute something to be meaningful. And so there's this idea to make other methods deep as well. So if you analyze neural networks, then you don't think that there's anything that is specific to neural networks, why they should be deep and other methods should not be deep. There's just an inherent, I think, added value to a method to pick up something compositional structure, and that means they have to have some form of composition structure built in. And one thing we did in a line of work is to construct a specific form of deep Gaussian process regression based on these earlier results that we had. And it's a hierarchical scheme that first somehow puts a hyperprior on compositional graphs, and then once you have picked a compositional graph, then on every edge you draw that from a Gaussian process. So Gaussian process regression is a huge, widely applied method in machine learning, and now more and more people see the advantage also of deep Gaussian process regression. It's hard to implement. It's much, much harder than the deep neural networks, which probably is a thing why they are not such successful yet in practice. But from the mathematical analysis, I think they have much nicer properties actually than the deep neural network. So they are somehow beneficial. And I see more and more work where people really try now with some clever tools from sampling theory, and so to make efforts to get to posteriors using deep Gaussian processes. We also have some results that shows that certain learning problems, that's a bit like related to this thing I mentioned before about wavelets. And for certain learning problems, just taking Gaussian process regression doesn't give you optimal posterior behavior in terms of convergence rate. You really need to take deep Gaussian processes to get to the optimal convergence rate. Okay, there's a gap, and somehow the depth is also for Bayesian methods is you have somehow to do some form of composition, which is interesting. Okay, then another line of work. So I think look for problems, which is a lot, like many think unexplored, or other graph neural network structures. Okay, so people really focus nowadays still on the feed-forward neural network. So I mentioned that these image deformation models, we can analyze convolutional neural networks, but there are many, many other network structures out there where we still lack complete, somehow some understanding, theoretical understanding. And it's interesting that many of them have very different properties, although they look like neural network, but suddenly the properties are very different. So last year I worked with some co-authors on graph neural network, and there you can see that just one or two layers are enough, so you don't need these log-n layers. So the theory is very, very different, and the role of depth is very different, and you see it in the theory why that is the case. And also the nonlinearity of the activation function has a completely different role. So there are, it's just not transferring these results to other network structures, there's always new effects in the other network structures. Maybe one thing you have been seeing, which is a huge success, are these Kolmogorov-Arnold networks, or CANs. They came up a bit more than a year ago. I checked this morning. I think this paper has already 1,700 citations or so. It's a really highly cited paper. And that actually builds on earlier theoretical results on the Kolmogorov-Arnold representation theorem that go back, of course, to Kolmogorov in the 50s. And then there's a whole line of work. I also contributed one article to that, where people have really wondered how can we link this Kolmogorov-Arnold representation theorem that somehow also shows that you can do functional representation via compositions of univariate functions, how you can link that to neural networks. And I think this is really a breakthrough. And so it's completely different than also the standard neural networks. It beats standard neural networks in many, many ways. I think it's a good example how theory can contribute, because without Kolmogorov-Arnold representation theorem and all this follow-up work, you could never have come up with these constructions, right? So it's not something you just invent as an engineer, or so you really need the underlying mathematics to come up with this thing, and it seems to be something like one of the probably rising. It's a rising idea, and it beats pins and standard neural networks on many tasks, and has many other advantages. It's interpretable and so on, and that's. But otherwise, I think. Like before the Kants, I was quite almost depressed, because I think the theory, when I started that, there was so much hope the theory can contribute to this development. And yeah, so in the end, there was so little. I mean, we can reproduce empirical findings with theory and so, but if you also listen to these talks this morning, and so in physics, there has been much more intertwining between theory and experiments, right? So theory would sometimes propose an experiment and vice versa. And here it's still driven mainly by experiments. So how can we overcome that? And that's something I hope to do by really thinking about what could come after deep neural networks. And so one of these paradigms is, of course, that over time they more and more resemble biological networks, the way the brain functions, and then they get better. And so that somehow suggests that the future of AI might be even more biologically inspired. One thing you have seen before, like the years of my work on sparsity of neural networks, biological networks are also sparse. I hope that at some point I can make use of all this knowledge. So I have this ERC grant that tries to somehow transfer results from the artificial neural networks to biological neural networks, and also work out what are really the unique and distinctive features of biological neural networks, why they can be better than artificial networks. And here, because maybe you follow this thing on your morphic computing, so, but it's really hard now still to train these biologically inspired chips. And I think here we can maybe really make contributions from a mathematical side that can be helpful later on to really train biological networks. Okay, so then you think, okay, isn't that the same? But these artificial neural networks, they differ from the biological networks in many ways, in terms of structure and also in the way they learn. So what's the difference in structure? The difference in structure is that artificial networks are deterministic objects and just send numbers around. But these biological networks are basically the stochastic object, if you want. So the input is always a spike train. That is, you can think about the Poisson point processor. So, and then you train somehow the output against spike trains, and the information is in the moments when these neurons fire. And so it's not in the numbers, but it's really in these firing times. And so, of course, that means a lot for like how they can do signal processing in a different way than, say, artificial neural networks can do it. That's one thing, the difference in structure. The other thing is the big difference is the difference in the learning. So artificial neural networks, we all know this is based on gradient descent, and all these ML work is basically on understanding properties of gradient descent. But biological networks, we know that they cannot be based on gradient descent, because gradient descent is a non-local method, and biological networks can only implement local rules. For gradient descent, you would need to know all the other weight parameters to update an individual parameter. The brain doesn't have the capacity to exchange all this knowledge, and so they have to be based on other learning mechanisms, and I'm working on that. So one can link them to so-called zeroth order optimization methods. But the thing with zeroth order optimization is that it's another form of noisy gradient descent, if you want. But it's very, very noisy, and the noise level is so large that it typically harms the convergence rates, and the larger the dimension kicks in. The dimension, the more parameters you have, will somehow enter up in the convergence rate. And so the way is now like, it's a bit like the thing 6-7 years ago when we started with neural networks. There was also sort of similar paradigm that we said, like, mathematical theory tells you that on high dimensional input spaces, no function learning methods should work well because we have curse of dimensionality. And by now we found some mechanisms on how neural networks can circumvent that. And here it's a bit a similar thing. So we have these zeroth order optimization methods, which are considered to be poor because they're so noisy and have provable poor convergence rates for a couple of problems. But so there must be some specific cases where they still perform well in the same way as a neural network can, or like an analogy with a neural network circumventing curse of dimensionality, that it can overcome these drawbacks of the biological network and somehow overcome that. And so we have some results where we can show also mathematically certain instances where they can perform like standard gradient descent methods. Okay, and that brings me to the end of my talk, and my time is almost up. Statistical theory, yeah, I think it faces a lot of non-standard challenges and really led to many new innovations in non-parametric statistics. I think one of the big, for artificial neural networks, the holy grail is really to bring the optimization and the generalization guarantees together. It seems almost infeasible, and maybe one could think about steps in between in such a program. And what I want to focus on in the future is this analyzing biologically plausible learning rules. Many of them have been proposed in the computer science literature by major people like Hinton or Joshua Benjo and so on, that just haven't been analyzed by theory people yet. And with this, I would like to thank you for your attention and feel free to ask questions. Thank you.
Variance decomposition on the slide 6.
Mm-hmm.
And I understand it as variance bias trade-off in a different context.
There's definitely, so it's definitely in the regime where you have bias variance trade-off, but this is not bias variance trade-off because that's optimization error. But now you ask in a case where this is larger than phi n, whether then the bias, I think then the bias dominates of the method, yeah. So it's, I assume you can understand it like a bias variance trade-off as well, yeah.
So skip layers.
Uh-huh. Like ResNet architecture, is it? Yeah. The ResNets, they will have the same issues, yeah. So for the denoising, they will have the same issues, yeah. They're definitely more stable in the deep regime and so on. They're easier to. You can see it as a sort of form of web parameterization of a neural network, but the web parameterization won't help you so much. I think it helps basically the algorithm, but yeah. So if you're on a level where you can understand gradient descent, I think then you can show benefits of ResNet. But on the level where you analyze basically something like empirical risk minimization, then it doesn't matter because you just reparameterize and the empirical risk minimizer will still be the same. Yeah. It's more than that, right? I mean, so this was a bit to illustrate, but.
Have you
Yeah, so we can also do rotations, of course. It's just a general A here. So we can also put, or we do also, yeah.
So
Mm-hmm.
this idea
I see. Yeah. Yeah. I never thought about this. Yeah. I mean, in principle, we can work here with somehow I didn't write it out, but with deformation classes and so you can restrict your deformations. For instance, you could say I only allow for rotations between angle minus pi over 4 to pi over 4 or something like that. And but I'm not sure whether that would help you to have somehow a range of possible deformation. I don't know where in the gene where the deformations should happen. Should they happen before you somehow have the thing you want to learn, or should they happen afterwards? Or so one would have to look closer into the specific application, I believe.
So thank you for the interesting talk. I have a question regarding the data generating process. That's this slide here. So what you explained seems very plausible for a problem like MNIST, but what about more complicated problems like image recognition? So there are indications empirically that it may be a hierarchical process giving rise to the construction of images, for instance. Indications can be seen in the data covariance matrix, which has power law spectrum, and so on. So are there results from mathematical statistics for this type of models?
Maybe one could combine it with these compositional structures that I introduced in the earlier part or so, but we can, our model is this, and the paper is like almost 80 pages, and so it's the common question that we get, like, can you do edges or like all sorts of like art of perturbations that you see in images and so on. I think yeah, I believe it's a good trade-off between, say, what is mathematically still tractable and what is somehow realistic, right? In the end, what you want is somehow a model that captures these things that have been empirically found in real applications, and you just have to do that to an extent. Like the simplest model, I believe, where you can see that's the one should analyze. Yeah. So we do have a problem with all these papers that they immediately get very, very long. Like this is really 80 pages, and we try to be very like condensed already. And so, and I do, of course, know that people like to have it even more general. And so, yeah.
Thank you very much for your talk. It was very interesting. So what I wanted to ask is that now if you consider, for example, transformer-based architectures or something like this, people often do fine-tuning when they apply their transformer on their own dataset. And typically, they do this fine-tune with some low parametric models like LoRa, for example. So you really have your model, which is pre-trained on a super huge data set, and then you perform very low parametric updates in order to improve your model for your particular data set.
Yeah.
Do you know about some statistical settings, statistical guarantees that underpins this framework? Or?
Yeah, I think that's the form of streaming PCA or so, the LoRa. So you make a rank 1 update to your problem or so. I think you should compare to the literature on streaming PCA, and yeah.
Yeah, but I mean, do you believe it's more question if it is possible to develop some guarantees that, okay, if you try to specify your model, which was trained on a really much larger data set, to something smaller but similar with a low rank model, is it possible to quantify somehow? I believe yes.
So you mean you want to put some transfer learning model on PCA or so?
Yes, something like that.
Yeah, that would probably be
transfer learning with
I saw some papers on the computer science literature where they do transfer learning with PCA. I don't know whether they use LoRa or so, but I think they just use some functionals or so, but it goes in this direction, yeah. And LoRa, of course, I have seen the paper. I think it's also 5,000 times cited. So it's a big success, and I think one has to analyze it also from a mathematical point of view. Yes. Good point, yeah. Yeah.
is it possible to establish the pointwise risk convergence or super convergence of neural network estimate?
Yeah, so for this empirical risk minimization theory,
Yeah.
it's almost impossible to go beyond, say, the loss that is induced by the Hellinger distance or the Kullback lidar. So that seems very closely tied to all these techniques that we use in empirical risk minimization. So I myself, I have one paper where we show that for a specific empirical risk minimization problem, you can get soup norm. Oh, you're not? Oh, yeah. Okay, yeah. So that's not soup norm. But then you see the techniques become quite different compared to standard empirical process theory, right? So it's based on a contradiction argument and some weird perturbation thing, and so that you have to do. And so I mean, for general theory, it would be interesting to do that, but I think it's also very, very hard. So we easily came to, we wanted to have it in a much more general framework, this Bernoulli paper.
Yeah.
But then we had to really just stick to smoothness at most one, because otherwise it completely failed. So it was just not possible to work it out anymore. And so I think there's not so much, or it gets very, very hard.
Yeah, paper of Bafu.
No.
His Bernoulli paper, he found that if we want to construct estimator with super convergence by empirical risk minimization, then the empirical risk should be modified as some kind of maximal of a criteria. So you should to minimize a maximal of a criteria to guarantee the super convergence. So I'm very